Hello to you from Chem Help ASAP. In this video, we will talk about color in organic molecules and why so many organics are either colorless or white solids. Our first task is to explain why small organic molecules tend to be colorless. The answer is in the idea that small organics usually do not absorb light in the visible spectrum. Liquid small organics are therefore clear, colorless oils. They look like water. The facets on solid organics reflect all visible wavelengths and therefore appear as white solids. Let's look at this visually. When and if absorbed, visible light causes electronic transitions, exciting electrons from a filled orbital to an unfilled orbital. In most organics, the energy gap between the filled and vacant orbitals is large, so large that visible photons lack the energy to bridge this gap. Maybe UV photons can be absorbed to excite the electrons, but we can't see the absorption of UV photons with our eyes. We only see visible photons, the color spectrum. A consequence of these ideas is that if you see an organic compound with color, often a yellow, brown, or orange hue, people will suspect that the compound has impurities because pure organics normally do not have any color. What is happening here? Why are impurities always brown, yellow, or orange? If a compound has color, then the compound or an impurity within the compound must be absorbing light in the visible spectrum. How can this happen? Well, the molecule must have a smaller gap between its filled and unfilled orbitals. The small gap allows an electron to absorb a lower energy visible photon. This absorbed photon tends to be more on the higher energy, nearly UV end of the visible spectrum. So the molecule absorbs in the violet, indigo, blue end and reflects red, orange, and yellow. Therefore, the color tends to appear more brown. From a chemical structure standpoint, the most common way to compress the energy gap between filled and vacant orbitals is through conjugation of pi systems within a molecule. So if you have a compound with a benzene ring, then maybe a colored impurity would have incorporation of a second additional ring. The larger ring system compresses the orbital gap and allows absorption of visible light. I will note that people are often very critical of impurities, but a very tiny amount of impurity can impart a lot of color. So just because a compound has some color, the material can still be very pure. Also, impurities often do not have color, so don't assume that something that is colorless has high purity. Ultimately, the absorption of visible light is connected to the structure of a molecule. Through chemistry, we can exploit this structure-function relationship and intentionally design molecules that absorb specific wavelengths and have specific colors. This is exactly how people design dyes for things like clothing, paints, and food. On the screen are 5 different dyes: FD&C red, number 40, red 3, yellow 5, and blue 1. FD&C stands for the Food, Drug, and Cosmetic Act of the US FDA. All these compounds, based on their degree of conjugation and functionality, have specific visible light absorption that results in a specific color. That's the story about color and impurities in organic molecules. I hope that you found this video interesting or helpful. Questions are always welcome in the comment section below the video. Take care.